thank you very much for the invitation. I mean, it looks like an absolutely fantastic program. I'm just, unhappy that I can't be here in person because I also had a very heavy schedule of teaching. But so what I want to tell you about, so it's this high-speed Fourier Ptychography. And so what we're using here is deep spatio-temporal priors. And so I should say this is work you at the EPFL, but mainly done by Pakshal-Bora, Tanhan, Yuxian Long, and Jae-Jun Yo. Okay, so those are really the ones who made it happen. And so let me maybe just give you the context. So the context is really about Fourier Ptychography microscopy. And as far as I know, this was pioneered by Zhang et al. In 2013. And so this is just the setup for getting a static image. And so the idea here is that what you do, you illuminate your sample here with one LED here. And so that will shine light here. And so at the level here of the specimen, so in the focal planes, so that this will induce a modulation of now the X of R is the thing you want to recover. But then you have this modulation with a plane wave. And now this plane wave depends on the geometry. So the location of the illuminating LED. And so then what you can do, you can shine on different LEDs, and then you will get here different modulation of the image here that you want to recover. So then there, what you have then is a objective lens of a microscope. And so then if you look in the Fourier plane, here what you will have is actually the Fourier transform of the object you want to recover. But because it was modulated, it will be shifted in Fourier. And then you also have the effect of the pupil, which will do this diffraction limiting of the microscope, but eventually also with a phase profile. And then what you have here at the exit here, you have again a focusing lens that will in fact do the equivalent of an inverse Fourier transform. And then also here, because you're measuring intensity here, in fact, you are getting the square. So the square of here, this measurement, which corresponds to the inverse Fourier transform of this thing here. So now the thing is, because you have here this pupil function, so what you will have is actually a kind of diffraction limited image. And so those will be, then what you will be collecting is several low resolution intensity images, and each of them corresponding here to the shining of a given LED. And so then at the end, what you have to do really is to solve a phase retrieval problem by considering all those intensity measurements and then apply all the mathematics of computational imaging to reconstruct now a complex value image of phase and amplitude. And now if you want to do that dynamically, now you see the problem is you have to modulate, with different plane waves. And typically what you have to do, let's say you have to acquire W such low resolution images. And then usually what one does, you will assume that the specimen wasn't moving while you are acquiring all those measurements. And then based on all those low resolution measurements, now you're solving your inverse problem with this nonlinear, because there's this square at the output. And then you're trying to retrieve here this amplitude and phase image. And so you do that for every batch here of W low resolution images. And so there what you see is, now if your object is moving, you obviously see that somehow you have a trade-off between spatial resolution, because to get better spatial resolution, you want to get more measurements. But then since all the measurements you have to process together to get one output of a time image, then of course if you have more measurements here, you will have a lower temporal resolution. and so now there are still like approaches to trying to make this Fourier ptychography more efficient. And I think several of the people actually are here in the workshop, so that's very nice. I would have liked to talk with them. The first way is by using optics. And so there's Tian et al. And also like Laura Waller's group. So there, the idea was actually to use multiplexing, so maybe to shine several LEDs at the same time, and also use the fact that the light is incoherent, so that you can get more efficient measurements. And then there are a variation on that theme. But my team, we are not optics people, we're really computational imaging people. And so we are more like on the side of trying, to get improvement by working on the reconstruction algorithm. And so you could say this is really an instance of compressed sensing. So if we want, let's say, to get higher resolution of lesser measurements, and so there the general paradigm is really to formulate the reconstruction as an optimization problem, as stated here. So maybe just to remind you, so the X is really this high resolution image we want to reconstruct. The H is the modeling of the optical system, the Fourier transform modulation, and pupil function. And then at the end, you have this squaring, which really makes the problem nonlinear. And so what you want to do is like enforce consistency with your measurements. And so this D here will be some loss function. So typically some measurement of the error. I mean, we will not use exactly the error. We will use something a little different. And then usually, like if you're trying to crank out more resolution, then you have measurements. Of course, this is ill-posed, and then you have to throw in some regularization. And so there I'm happy that actually with Stan Osher, that's part of the conference. Of course, I mean, the most famous way of regularizing is total variation. And then there's no surprise that actually people relatively early on started using this regularization and total variation in trying here to address the ill-posedness of the problem when you're trying to reconstruct at a faster rate than your data rate. And then there's also like, variance of imposing group sparsity, and also like this plug and play algorithm with BM3D here, which is also the kind of methods that we people are using for solving all kinds of inverse problems in imaging. And so all those methods actually are applicable here. Okay, with the twist here that this is actually a more difficult inverse problem because there's this square here. And okay, so this is, let's say, what happens on the compressed sensing front. And then not surprisingly, in fact, now that everyone is using deep neural networks, then there were also people who have applied nonlinear, deep neural networks to try to do some direct nonlinear reconstruction. So there are a few papers that are mentioned here, and also using generative priors. So maybe what I should say that the initial algorithm here for reconstructing this ptychography images actually is the Gershberg-Saxton algorithm that was proposed like in the first papers. And so it doesn't use regularization, but solves this phase retrieval problem. Okay, so that's more or less, the situation right now. And now the question is, can we do better? And you see here, if I look at the conventional paradigm, is just to require a diversity of measurements, like using different of those plane waves with the illumination. and then pull them together in order to make a reconstruction. And so this yields then frame-by-frame reconstruction. But of course, here you have a downsampling rate of W, which is the number of measurements you need to acquire to do a reconstruction. So now what we are trying to do, so it's a little more daring. We're trying actually to reconstruct at the rate of the measurements. So every time you take one of those modulated images, low resolution image, now we want to reconstruct exactly at that fast rate. And so how can we do that? Of course, then you have a very ill-posed problem. And actually, if you want to do high-speed Fourier Ptychography, I guess you can only do that if you're exploiting temporal dependencies. And so there's been prior work here by using low-rank techniques in time. So a little in the spirit of principal component analysis. So imposing low rank, in the time direction. And so which brings you in some regularization. Now, in the present work, what I want to describe to you is actually a variant of deep prior. And so this is a method that uses convolutional neural network as regularizers, but we're bringing in a twist because we're actually having a spatio-temporal regularization, and that's absolutely the temporal part of the story is absolutely crucial so that we can reconstruct at a faster rate. Now, what I should say also that there's no training data required, which is a little strange for a deep neural network, but it's not so strange for deep prior. Actually, that's part of the paradigm. And then the framework is general enough so that you can also calibrate the system and estimate the pupil function as part of the optimization. And that's also what we're going to do. Okay. So let's go back a little to the physical model. So that's what I had just described in the first slide. So here, actually, what we're imaging here with the objective lens of the microscope here is this modulated version of the signal here with a plane wave, as I said, that depends here on the illumination and on the LED here. That is because you can switch on different LEDs, and so that will induce different plane waves here. And so you have L such LEDs, and so you have some underlying wavelengths, lambda also. And as I said, there's one LED switched at the time, and so that will then result in this model here. So the modulation is just this multiplication with the complex sinusoid in space. Then you do the Fourier transform, and so here again you're in the pupil, so in the Fourier plane. Then you apply the pupil, which will, if you look at it mathematically, it will just extract a part of the Fourier spectrum. But now with the modulation, you may shift the Fourier spectrum around. So that just means that you are here essentially measuring part of the spectrum. And then what you do here is the inverse Fourier transformation, which is represented here, and at the end, this square modulus. Okay, so now what we need to do to put that in an inverse problem, we just need to discretize just what the physics that I just described to you. And in some sense, so that's just going over the model again, but now with our notation. So the image that we want to reconstruct, we call it X. It will be complex, and it will be an image of size n by n. And so we stack all that in the vector, at least symbolically. And then we're getting those measurements. We call them Y. And now they're also images of size m by n, but m being smaller than n. And in fact, we have this upsampling factor that we want to do in our reconstruction. And so we want to reconstruct clearly images that are at a higher resolution than those measurements, but the idea being that we're collecting multiple measurements. And then now the pupil function, okay, the pupil function is really acting at the output of the microscope, so it's acting on those measurements. And so the pupil function, which will apply in Fourier domain, but we will also represent in a discrete fashion by a m by m complex image in Fourier domain. Okay, so that gives us here this discretized forward model. And maybe it's just recap here, but I think here the notation is important. So this is the input image. Remember, it is a high resolution thing. Then we do a Fourier transform of the size of the image. So n by n, fast Fourier transform. And then there's the action of the pupil also after modulation. And so this you can actually represent as a mask that will crop out a part of the Fourier transform. And actually this cropping here will be of size m by m. Okay, so, and that's important because it will be computationally more efficient to work with something, that is smaller here. So here we're of size m by m. We apply the pupils so that we can also mathematically represent by a diagonal matrix. So in the Fourier domain, so that's just the transfer function here. And then at the end, we do this inverse Fourier transform, but here I insist it's an inverse Fourier transform, but of the size here, of the smaller size of the output image, which will be here the measurements. And at the end, of course, you have to do your squaring. And so this can be done relatively efficiently just using Fourier transforms and croppings. Okay, so that's your model. And now if we want really to set up this as a inverse problem, so maybe you have to look the other way around. So here have the images, and so those, I should say, those are phase and amplitude images. Okay, and so here are some examples, and so those would be images that we want to recover that happen at the fast rate. And now for each of those complex images, actually we're just extracting one measurement, okay, which is a modulation with a given plane wave, and you know all this in going through the Fourier, etc., but giving us a low resolution image. And so here really the challenge now is, given all those low resolution measurements, which are the y's, and with their corresponding time stamping, so this actually physically there's no like rebinning or anything, so we're really trying to reconstruct at the rate of the measurements. So now we want to reconstruct the X, but which are a higher resolution. And so now, well, what is this method of deep prior? Okay, so that was introduced by Ulyanov, 2018. And it is a sort of generic method that can work for almost any inverse problem. And so inverse problem being like, say, y equal hx, where h represents the physics, but initially designed for linear inverse problems. And so here, what is the concept? Here, the concept here is that somehow you're choosing some latent variable and low dimensional space, and this latent variable you are generating random. Okay, so you are generating this z, which is a random variable in low dimension, and then you have this neural network, which is a convolutional neural network that will transform this latent variable in some image. And now, of course, you want this image to be faithful to the data, and actually that's the trick. Okay, so then what you are going to do, starting from the z here, okay, you apply your neural network, and then you apply the physics, and you want to obtain something that is faithful to the data. And so then you will actually train your neural network until actually what you are generating from this fixed latent variable will be as faithful as possible, like in terms of this fidelity, data fidelity function, as faithful as possible to the measurements. And then once, you're happy with the convergence of your neural network, then you just actually look at the output here of the neural network applied to the Z, and then here you can just read off the reconstructed image. And so why does this work? It's actually not so well understood, but it's because convolutional network, they generate stuff, images actually that tend to be natural looking, and this is because of their architecture, okay, that involves like sort of wavelet-like convolution operations. And so it tends to favor natural-looking images, at least over noisy images, and so noisy images, which would be the output of ill-posed inverse problem. And so there's also some know-how you need to apply early stopping to avoid overfitting. And in some sense here, the trick is that it is the architecture of the CNN plus this optimization procedure that I just described to you that does implicit regularization. And that's the reason why this is called deep prior. And the thing is, this works amazingly well. And I must confess, not so well understood why it works, but I will show you the results, okay? But now this is the conventional deep prior. So what we did here is a spatio-temporal variant of this deep prior. And now the idea here is actually what we're having is actually a dynamic sequence of images. And so instead of now having, a random latent variable for every image, now we are forcing the input of the neural network actually to lie on a low dimensional manifold, and that's actually parameterized by time. And the simplest manifold is actually what we're using in our experiment. We make them lie on a straight line. Okay, so we are sort of injecting now, and this neural network is actually shared by all images in the sequence, and we're just injecting here some latent variables that lie on the straight line. And so now the neural network will do its job in generating images, and because the inputs here lie on a one-dimensional manifold, then a good hope that actually the outputs of which are images somehow will also lie on the manifold, and that will then be indexed by time. Okay, so how are we now solving this problem? Now we are just solving it as a global optimization problem. So now the thing is, this neural network is not a neural network in space and time. It's only a neural network in space. Okay, so it's applied to every one of those fixed inputs that we're presenting to the algorithm. Then here we are having the physics, and now the system matrix, of course, depends on the lead that is being led at the moment of the measurement. Okay, so every time a point here has a different system matrix, and at the end, of course, we are here measuring the squared amplitude, and we're trying to fit that to the data. And then, okay, we're training the neural network so that it will adjust its parameters so that all this, it produces outputs that are consistent with the measurement. And so at the end here, if we just apply the trained neural network to each one of those inputs, we were able to generate the time sequence at a finer rate, but those axes also having high resolution. Now, the choice of the latent vector here, the idea of being on this manifold and is just like, as time moves, actually the image doesn't change too much. And so like two close time points, will be relatively close in latent space, and that somehow will also map into closeness in the spatial domain. So here, just to recap, we have the CNN architecture, the shared network, and the latent space design that will give us our spatial-temporal regularization. Now, of course, let's get to the implementation. And so what's very important here is the network architecture, because this is what does the implicit regularization. And so here we're starting from something small, like in latent space. So it's a size, let's say, 8 by 8. And then applying here a bunch of convolution modules with batch normalization and ReLU nonlinearity. And so here we have typically of the order of 32 or 64 of those convolutional filters. And we're also doing 2 in succession. And then what you do, we progressively augment the size of the image here by 2. Again, like applying convolution, but now everything is larger by factor 2. Then again, upsampling by 2. And applying another bunch of convolution, batch normalization, nonlinearities, etc., until you get to the size of the desired size of the output, which amounts to upsampling by a factor 32. And then at that level here, so we feed that in actually 2 branches. There's one branch which has a convolution network and a d-ReLU, which is this function here. So it's a slight perturbation of ReLU, but that is adapted to the fact that we want to produce something that is positive, and so a magnitude. And then there's another one that will produce the phase, and there we have an arctangent here to produce a phase that is between minus pi and pi. And then you all put that together, and then here you're outputting a complex image, and so then you can you can visualize either the magnitude or the phase. Now the optimization strategy, so there is a little twist here, is not use the standard least square criterion. And so this is also like inspired by prior work, but in another application, not ptychography. So using a square root applied to the measurement, and there's a small bias here, to adding a constant. And actually, the reason of the square root, actually, this goes very well with Poisson noise, because it's also related to the Ascombe transform, which in fact takes Poisson noise, and after square rooting, this will transform into stationary Gaussian noise. And so there's a little of this idea here. So we're applying this square root, before doing the least squares here. So then it is super important to initialize your neural network well, and we call this warm start. And actually, to that end, what we're going to do is we're just reconstructing a low-quality reconstruction using a standard frame-by-frame method. And so that would be this reconstruction. And then actually to initialize the neural network, now we are training it so that it can fit this not-so-good reconstruction. Okay, so this is a initialization optimization. And then we go on with the global optimization of the scheme using Adam-based mini-batch stochastic gradient algorithm, okay? So which is also a relatively standard technique used for neural networks. Now, okay, I told you we in principle, the scheme allows us to auto-calibrate and to recover the pupil function. Here again, we're using scheme inspired by prior work, including also work in Laura Waller's group. Here, the pupil function we will represent with Zernike polynomials, and usually relatively few Zernike polynomials. Typically, we're using 9, which are represented here. And so the Zernike polynomials, so we're taking the lower order Zernike polynomials that are represented here. And so those Zernike polynomials, they're separable in the row here, which is the radial frequency, and theta, which represents the phase, okay, the direction. And so we are representing now our pupil function as a, exponential of, those Zernike polynomial with some coefficients here. And so the unknown here for the pupil are those Zernike polynomial coefficient. I mean, it's inside of this exponential, but this is differentiable. So this can be optimized by using Adam type auto-differentiation algorithms. Okay, so now the joint optimization. So what we need to do, given the Zernike polynomial, first we have to, produce this pupil function. And then here we have the forward model, which is, the one I described before. So Fourier, this cropping, applying the pupil function and inverse Fourier transform, and at the end, taking the square. And then if you want now to do the whole thing, now reconstruct the images as well as the Zernike polynomials or other parameter of the optical system. So you're just solving this global optimization problem. So there's first like optimization over the neural network. So it's the same neural network shared for the reconstruction of every frame. But I mean, the cost function is now globally over the whole sequence of images. And at the same time, we're also trying to reconstruct the Zernike polynomial. And there are a few like mine, and they're also shared by all images. Okay, so now here are the numerical results. And I should say all this is a simulated setup. And so here is the setup of the LED array. And so now, depending on the position of the LEDs, here we have 100 LEDs, and with those geometric spacing, etc. And so there's also like, a corresponding numerical aperture here that corresponds to the amount of light that actually you will capture at the level of the object. And of course, this is also assumed to be relatively far away, so that you can assume here that this will induce a plane wave at the level of the specimen. And then the objective, so we have a numerical aperture of 0.1, and we're also like putting in some Zernike polynomial coefficient just to demonstrate the possibility of recovery also of those system parameters. And so this would be here the frequency, the wave numbers of the plane waves, originating from those individual LEDs. And so here's also the pupil function. And so the pupil function here, it is a pure phase distortion because the amplitude here is a constant. Okay, so here are some example of ground truth. And so the ground truths are actually what we did. We kind of fabricated the ground truths, but using some real data. So there's a real data that comes from a challenge, a tracking challenge. I think that was given at the ISB conference. And so what we did with those images, which are a sequence of dynamic imaging images, then we also simulated actually. We assumed the images are relatively flat, so thin, and so we use those images as the refractive index, and then we generated, using a beam propagation method, some realistic phase and amplitude images, so that would correspond to this dynamic sequence. And so they are shown here. And here are also shown the low resolution measurements. And of course, those look very diverse because, of course, it depends now on the selection of a particular LED, and which then induces a certain modulation. And maybe to show you the data. Okay, so those are the moving images, amplitude and phase. This is the measurements. And so here this shows here how you're moving around your pupil in Fourier domain with this modulation. And actually what you are capturing as data here is what falls inside the circle. And then the goal, of course, is to reconstruct everything. Okay, so now we have to compare some methods. So the baseline is the Gerber-Saxton algorithm, and so which is the standard algorithm. This one is not able to do any pupil estimation because actually there's no explicit optimization here. Then we have a data consistency estimator, and so this, I would say, it's maybe a slight refinement on the Gerber-Saxton, because here we're sort of framing that as an optimization problem, but which allows you also to estimate the pupil parameters, but there's no regularization. And then, of course, the workhorse of inverse problem, regularization, total variation, and so we are having the same data term here, but imposing some total variation both on the amplitude and the phase. And here are the results. Okay, so that's the ground truth. Gerber-Saxton, and you saw this ringing artifact. This data consistency doesn't do too well. And actually, those don't do so well because actually they don't have so much data to reconstruct from. The total variation maybe does a little better, but it's still not so high resolution, and that's the output of our reconstruction. And so here, likewise, for the phase image, and so you see that actually the reconstruction is pretty good here. It looks very much like a cleaned up version of the ground truth. And then you can, this is static, okay, at a given time frame, but then we can also look at dynamics. So let's take along this line here and look at the variation in time of this line here, okay? So, and this is here, this, the line changing in time. So this is with respect to the ground truth. Now, if you look at here, it's sort of not so good. Lots of noise. Here also with the total variation, it gets a bit lost. It's also a bit normal because there's not so much regularization along a temporal dimension. And so with our technique, and so you see that it's really not static. You see that there are changes in time. And so I think the best is seeing the results. And so this is the sequence of reconstructed images. So using, let's say, Gerber-Saxton here as a reference method, and you see all those artifacts. While with our reconstruction, actually you have relatively good quality, and you see the object moving. Okay, and so you really recover the motion that was in the original image without artifacts. Okay, now the question of this you saw visually that it looks much better, but then we can also look at the signal to noise ratio, and there I must say there's an amazing 10 dB improvement over the other methods. You could say a little due to the magic of this deep prior, okay, that induces this spatio-temporal regularization. Then the next thing was to also test our ability to recover the pupil function. And so there's the output. And so here you see now, if we compare with the previous one, for example, Gerber-Saxton, you see that because now the pupil is incorrectly not taken into account. I mean, it's wrong here, so that will, of course, induce distortions here. And actually, those methods are not really able to correctly estimate the pupil, while the proposed algorithm that's almost as good as in the previous case, so it's able to reconstruct relatively nicely. And now if I show you the video, so I think you will appreciate the quality of those images compared to the others. So now, yeah, I would say that total variation does relatively well, with the phase, but not so well with the amplitude. Okay, so now if we look at that experiment, so how well did we estimate the pupil? So here are in blue the exact Zernike coefficient of the pupil, and so in gray it's the one that is recovered by our algorithm, and so the others are actually not so able. Actually, this data consistency doesn't get the pupil at all, and also the total variation. I mean, gets a little in the direction of the pupil, but actually doesn't do such a good job. So here we have even, a stronger advantage because we're getting the pupil right. And there, if you look at the signal to noise ratio, so it's, I would say, comparable to what we had when we knew the pupil. In fact, we're only losing 1 dB as a cost of estimating the pupil, but visually it looks almost as good. And we do a fairly good job at estimating the pupil compared to the other methods. Okay, and that really gets me to the conclusion. So what I wanted to demonstrate to you is the feasibility of this high-speed Fourier Ptychography. And this is really doable because we can exploit those temporal dependencies. Now the proposed framework, now we have a generative CNN to impose spatial regularization, because this will just, sort of generate sort of naturally, in quote, looking images. But now there's this coupling with the temporal manifold that we specify in latent space. And this is the thing that really makes it work over time as well. And that's absolutely crucial here in exploiting these time dependencies to be able actually to reconstruct with a good spatial resolution. And so, I mean, this is the principle here. Shared CNN latent space design is able to induce this spatial temporal regularization. Now, the advantages, I would say there's impressive performance improvement in the low data regime. And that's what we're after. We want to do this high-speed imaging. There's no training data required, and it can also include the estimation of the pupil. So I'd like to thank also the ERC, so it's the European Research Council for partially funding this research. And maybe now, because I'm close to the end, I'd like, I would have really loved to be part of the conference. And there's still a member of my team, so Jonathan is here. And presenting a poster. And I think it's a very nice poster because it's sort of very, very nice overview of, all the different type of imaging that you can do using phase-retrieval. And so I really encourage you to go to the poster. And of course, one of those modalities is the Fourier Ptychography, like I was discussing here. And now, last, I'd like to mention some references. So for those who are interested, just send me an email, and I can share with you our manuscript here, which is currently under review, which has the details. Otherwise, there are lots of references here to the pioneers, the people who did the optical setup, and all the people working in computational imaging, having applied that to the ptychography. And then there are also some references for deep prior. And I should say there's also work in our lab where we applied that to MRI with actually good success, where we almost obtain as good improvement as what I'm discussing here. And I think this concludes my talk. And it's maybe best that I stop sharing if there are questions.